This is an illustration on how to solve for the pH of a salt of weak base and strong acid. Let us first discuss about a particular type of chemical reaction, which is neutralization reaction, or also called acid-base reaction. For acid-base reactions, the reactants are acids and bases. The products are salts and sometimes water. There are acid-base reactions wherein water is not formed. For classification of salts, you probably encountered these terminologies in your study of chemical equilibria. Salts will be classified based on what type of acid and base that made them up. So for example, number 1, a salt of strong base and strong acid are actually made up of a strong base and a strong acid. So if we predict the products for this reaction, it will be sodium chloride and H2O. So the salt formed in this chemical reaction is NaCl, and NaCl is in fact a salt of strong base and strong acid. For number 2, this salt is made up by combining a strong base and a weak acid. Now here, the reason why the list of strong acids and strong bases are shown here, and usually you're asked by your teacher to memorize this list, is because the list of strong acids is relatively short compared to the longer list of weak acids available out there. If you want to see the long list, if you want to see a list of weak acids, check the appendix section of general chemistry textbook. You will see a long list of weak acids there, also given their ionization constants. So for this example, let us use the following weak acids. Let's say nitrous acid. So this one is nitric acid, written here in this table. So this is nitric acid. This one is nitrous acid. Nitrous acid is a weak acid. Another one is acetic acid. Now for weak base, to make it easier, let us use ammonia. Okay, so salt of strong base and weak acid, we will be using nitrous acid. So the product for this acid-base reaction would be sodium nitrite plus H2O. Sodium nitrite is the salt form in this reaction. It is classified as a salt of strong base and weak acid. Okay. For number 3, which is what we're going to focus on in this video, because we're going to do computation for number 3, let us use the example salt of weak base. Let's see, weak base that we will be using here is ammonia, and then the strong acid will be HCl. So the product for this acid-base reaction is ammonium chloride. So ammonium chloride is classified as a salt of weak base and strong acid. And in this reaction, in this acid-base reaction, water is not formed. So for salt of weak base and weak acid, you can just combine these two. Okay, so HNO2 plus NH3, you will form ammonium nitrite. So ammonium nitrite is classified as a salt of weak base and weak acid. So for this illustration, again, we will be computing for the pH of a solution with this salt, ammonium chloride. Suppose we have 0.1 mole per liter concentration of ammonium chloride. So to make this solution, let's suppose we have 1 liter of pure water, and then we place 1 mole of the salt ammonium chloride. Okay, so we will assume that there will be no change in volume. So this will be our initial concentration. Okay. Ammonium chloride is a soluble salt. I encourage you to look at a solubility table. So according to solubility tables, if you have a salt wherein the cation is ammonia, it is generally soluble. And also if you have a salt wherein the anion is chloride ion, it is generally soluble. So this salt, ammonium chloride, is generally soluble. So we expect, for a dilute concentration, we expect complete dissociation of this salt. to form its component ions, ammonium ion and chlorine ion. So once these ions are present in water, it will be interacting with the species present in water. Of course, that will be H2O, but H2O also undergoes partial ionization to produce its component ions. This is called auto-ionization of water. So wherein water will ionize to produce hydronium and hydroxide. So in a neutral solution, these two are produced in equal amounts. So let's try to write the reaction for the auto-ionization of water. So the double arrow indicates the partial ionization of water, forming only a small amount of hydronium and hydroxide. So the equilibrium constant value for this is 1.0 times 10 raised to negative 14, and the expression is the concentration of hydronium and hydroxide. Brackets indicate that the value you should place here is the mole per liter concentration, molar concentration. So given this small value, you can say that there's only a small amount of hydronium and hydroxide being formed. So in water, of course, the predominant species is going to be water molecule and a small amount of hydronium and hydroxide. Now, once again, we said that we will start with 0.1 mole per liter of ammonium chloride. So this is the start, and then during the reaction, all of this will be dissociated to produce ammonium ion and chloride ion. So final, this is going to be 0, this is going to be 0.1, and then this is going to be 0.1. Let's see how these two ions will interact with the species present in water. Let's start with chloride ion. So if these two interacts with each other, notice that both are negatively charged ions, so we expect no reaction to occur between these two. So how about chloride ion and hydronium ion? So to check that, let's write the two. Let's see if a reaction can occur. So let's suppose both are reactants. What will be the products? So hydronium is an acid, so it can donate hydrogen to chloride ion to produce HCl, and then after donating that, we will be producing H2O. So HCl is formed. Okay, how about chloride ion and H2O? Okay, so as you can see from the previous one, positive, negative. This one, positive, negative, neutral. This is a base, and water here will act as an acid. We will be forming OH minus, and we will be forming HCl. So for both reactions here, we dismiss the possibility of this happening, and we take the possibility of these two happening. So in both cases, HCl is formed, but according to this list, HCl is a strong acid. So when you say strong acid, it is a strong electrolyte, meaning it will undergo complete ionization. Either you represent this ionization in terms of the Arrhenius representation for the ionization of acids. So H plus will be formed, Cl minus will be formed. Okay, so here chlorine is formed again, and it is the reactant here. Okay, that when you form HCl, because HCl is a strong electrolyte, it will ionize immediately to form hydrogen ion and then chlorine ion. So because of that, we will consider chloride ion as a spectator ion. Okay, so let's clear the screen, and then now let's see what will happen if ammonium ion will interact with the species present in water. Now let's see how ammonium ion will interact with the species present in water. So first, let's try ammonium ion and hydronium ion. So these two are both positively charged ions, so we dismiss the possibility of these two forming a reaction. So how about ammonium ion and hydroxide? So positive, negative. Let's write the possible reaction for these two. So here, ammonium ion. Ammonia is a base, but ammonium ion is an acid. So it can donate hydrogen ion or proton to hydroxide ion. So this will form ammonia and H2O. Okay, so how about ammonium ion and H2O? So let's write the reaction for that. Once again, ammonium ion acts as an acid. This one, water acts as a base. We'll be forming ammonia and hydronium. Okay, so this should be double arrows because once ammonia is formed, ammonia undergoes partial ionization to produce ammonium ion. So this is a reversible reaction because ammonia is a weak electrolyte. So yeah, weak electrolyte. Some of it are present. So there's a certain amount of ammonia present. There's also a slight ionization to produce ammonium ion. So between these two reactions, ammonium ion reacting with hydroxide and reacting with water, which one should we focus on in order to simplify our computation? We will be focusing on the second one, ammonium ion and water. Why? Because first of all, as mentioned earlier, water is present in larger amount compared to hydronium and hydroxide. Remember the value here, this is very small. If you multiply the concentration of these two, this will be the product. That means there's a small amount of concentration of these two, hydronium and hydroxide. So we will focus on the species present in larger amount, which is water. So once again, water is present in larger amount, so that will be the one that is present to react with ammonium ion. Okay, so over here, we will write the reaction. So if you inspect this chemical reaction, notice that hydronium ion will be produced. And we know that from the formula pH is equal to negative log hydronium, concentration of hydronium ion. If we increase the concentration of hydronium ion, that will result to a lower pH. So as early as now, you can predict that the pH that will be the pH that we will have for this salt, if we dissolve it in water, will be acidic, lower than 7. Okay, so that is our prediction. Let's get an actual value for that pH. So once again, we will start with 0.1. Okay, so 0.1, this one. So we will start with our initial concentration, 0.1. Water won't be part of our equilibrium constant expression because it is it has an activity of 1. So for ammonia, this is going to be 0. For hydronium, there's actually a small amount of hydronium concentration, but we will treat this to be 0. So there will be a change. There will be a slight ionization of the ammonium ion, and then there will be a slight formation of ammonia and formation of hydronium beside the one that is already present. So at equilibrium, it's going to be 0.1 minus x, x, x. And then let's write the equilibrium constant expression. I hope you can see this. I chose purple ink. So let's write the ionization. Let's write the equilibrium constant expression for this reaction. Products at the top raised by the exponents, raised by the coefficient. So here, this is already a balance. Our exponent is 1. And then the other aqueous product over the concentration of ammonium ion. Okay, so the problem is we don't have an actual value for this equilibrium constant expression. Okay, what we do know is from available data, from available references, I'm talking about the appendix section of chemistry textbooks, we do know the ionization constant or equilibrium constant value for ammonia. And that equilibrium constant value, Kb, is 1.8 times 10 raised to negative 5. We know this value. Okay, but this value pertains to the chemical reaction NH3. This value pertains to this reaction, and the expression is Okay, so this is what we have. This is what we need. But the thing is that if you look at the equilibrium constant expression available to us, so we have a ratio here, NH4 plus over NH3 plus. This one, they are, this one is above, this one is below. So we can do algebraic manipulation here. I want you to notice that this expression is equivalent to, okay? So I want you to notice that this expression here is equal to this. What we did here is that we just transpose this variable up, this variable down, and then this number down here. Okay, so these two are equal. So the reason why we did this is because we can now replace with this one wherein we have a numerical value and then we have OH minus to see what will be the outcome of this substitution. OH minus over 1.8 times 10 raised to negative 5. And then the concentration of hydronium ion is retained. And now we have an easier equilibrium constant value to be solved because these two, the product of the concentration of hydronium ion and hydroxide ion, actually has a value. It is written here, Kw. And we can actually, this is times 10 raised to negative 14. We can actually get a value for this one, 5.56 times 10 raised to negative 10. Okay? So we can now solve this problem. So once again, this equilibrium constant expression, which is based on this reaction, has a value. The equilibrium constant value is 5.56 times 10 raised to negative 10. And we can now solve for x, which will give us also the concentration of hydronium. Okay? As a result of knowing the concentration of hydronium, we can actually substitute it here and get the pH. Okay, so this is how we're going to do it. NH3, the value for NH3, we will be substituting this with x. Hydronium, this one is x. This one is 0.1 minus x. So let's rewrite this, x squared, x times x. Okay, so 0.1 minus x is equal to 5.56 times 10 raised to negative 10. Solve for x. Again, solve for x. X is also the concentration of hydronium ion. So the value of x is 7.45 times 10 raised to negative 6. This is the value that we will place here in order to get the pH. And the pH is, what did we predict? We predict a pH that is less than 7, and the value of this one is 5.13. So for a salt of weak base and strong acid, this is acidic. So you can actually do the same computation for other salts of weak bases and strong acids. Okay, so what we're dealing here with salts of weak bases and strong acid is that the conjugate acid pair of the weak base, okay? So for salts of weak bases and strong acids, the conjugate acid pair of the weak base is the one that affects the pH. And then, since this one produces hydronium, it results to a lower pH or an acidic solution. So if you're dealing with a conjugate acid-base pair and you only know the value of the ionization constant for the other one, you can get the ionization constant for the other pair by using this expression. Kw, the value of which is 1.0 times 10 raised to negative 14, is equal to the product of the ionization constant for the base times the ionization constant of its acid pair. The same is true if we apply it for number 2, which is commonly given as an example. So for here, we know Kb, the value of ionization constant for ammonia. We also know Kw. We can easily solve for Ka. Again, you can do the same for number 2. So this is a series. I will be doing examples for the other types of salts of weak something. So there you go. I hope you learned something in this video. Please subscribe, please like, please share this to someone who needs it. Okay, so with that, thank you for watching.